Alrighty, welcome back to 344. So better locks. Like the previous lectures, some of this is review, some of this is newer stuff that you may not have realized how locks are actually implemented. So again, kind of review-ish. So we'll have some overview of locking implementations. I know some of this is 344 because I just did it. Go over what spin locks are. Hopefully you can implement a spin lock. The cost of locking, now that we can, analyze our performance a bit. Go over ticket locks, queuing locks, MCS locks, and some parallel programming techniques, which will be fun. So, more review. So, processes communicate IPC, different types of IPC, pipes, sockets, signals, shared memory, things of that nature, named pipes, all of those fun different things that are just essentially using a file descriptor and read and write bytes. So the main thing that threads use to communicate is just shared memory. Everything's in the same address space. They all use the same virtual addresses. They all map to the same physical memory. So since we have multiple threads all in our process, we need to ensure we don't have data races. And if you need to review, data races, 2 or more concurrent accesses to the same location, at least one is a write. So if we have that, we might have data races, and in which case we need to prevent data races using mutexes and things of that nature. And if we need to ensure ordering between threads, we can use barriers, condition variables, semaphores to ensure ordering. Use locks to ensure mutual exclusion. So, how are locks implemented? What's the cost of locking? And how can we develop more efficient locks? That's our topic for today. So, on uniprocessor systems, aka you just have a single core, well, within the kernel, if you have data shared between multiple threads, the only source of concurrency is context switching, so you simply do not do it. That is a very easy way to ensure that we don't have 2 concurrent accesses if we disable concurrency. Unfortunately for you, everything has multiple CPUs now, so that is something you could have done, in like the 2000s and below? But you can't do that anymore. So you might, be like, hey, okay, even with that, what about if we have an interrupt handler that we don't want data races in? Well, then in the interrupt handler, you can just disable interrupts, disable context switches, and then, it's just something else you have to disable. At a user level, you could just use blocking locks implemented by the kernel using those mechanisms above because, well, you can't disable hardware interrupts by yourself. That's the whole point of a kernel. So you have to ask the kernel to disable them for you. And this works because, well, nothing can happen in parallel. We only have concurrency if we only have a single core, but who cares about this because this is not the world we live in. So we have multi-processors and, well, we have true concurrency, aka parallelism. So code can actually happen simultaneously across CPUs at the same time. If you disable interrupts, that only affects the core you are running on, and it doesn't really disallowing context switching doesn't help if you have multiple threads either that are just executing, so that doesn't help you anywhere. So we need some help from the hardware, which should also be slightly reviewed from 344. So there are some hardware atomic instructions that we use to implement all of our locks. So the main ones are something like test and set. I can atomically test a value and set it equal to 1, or compare and swap. So I can given some memory location, I can try to compare that value and swap it if it has a certain value. So those happen atomically, which means they either happen all at once or not at all. No data races with atomic operations. So some other atomic operations we have: set, increment, decrement. We can do that atomically. And, well, if we want to have mutual exclusion, that requires some locking, and we need to use these instructions to implement spin locks. So here is some pseudocode for all the atomic instructions. Again, you just assume either this function runs or not. So it can't halfway complete. So test and set, what that will do is it will always return you the original value it read, and it will try and set that memory location to true and then tell you whether or not it was true before or false before. And again, does that atomically. Fetch and increment, same idea, except it just increments the value instead of setting it to true. And then compare and swap. Compare and swap will only set the value from old to new if the current value is old. So you could say most of the time it's used in Spinlocks where old is 0 and new is 1. So only swap the value to a 1 if it is currently a 0. Otherwise, do not swap it. And if it was already 1, well, you'd get the original value. Or some implementations just tell you whether or not it was able to swap it, yes or no. And then we have fetch and store. That will just give you the old value back and write a new value to that location. So those are all our fun atomic instructions. So Spinlocks, the easiest implementation for a Spinlock that actually works to ensure mutual exclusion is in the acquire. Well, you just have test and set. So while test and set, so while the current value is true, that means someone else has the lock, and I keep on trying to set it to true over and over again from false. If I was able to set it from false to true, then test and set would return false. That means I was the one that atomically changed it from false to true, so I have acquired that lock. And then in the release, well, I'm the only one that has access, like I'm the only one that has made it equal to true. So I'm the only one that can pass this lock call or this acquire call. So I don't need to worry about data races for the release. I just set it equal to false, indicating that I have now unlocked it and won't do anything. So this is a perfectly good implementation, and well, we might actually use it in some conditions versus blocking locks. So if, I have nothing else to do, sure, go ahead and use it. If the expected wait is really short, so some other things I could do that should be reviewed from operating system courses. If I don't acquire that lock, maybe I put myself to sleep for a little bit of time. Maybe I run something else, or just context switch to something else. Hopefully it can go ahead, finish whatever it needs to do, and finish the lock. So that will take some time. So if the amount of time expected wait time is lower than that, just try it again and hopefully nothing will happen. Or in some cases, you aren't allowed to block, like if you're writing an interrupt handler or something like that. So this is an implementation of Spinlocks. Everyone okay with this? Because the rest of the time, we're just going to talk about how to make this better. All right, so Spinlocks, pretty easy. So that test and set operates on memory atomically. It has to, the hardware implementation, relating it back to the caching coherency stuff, have to do like a read exclusive, invalidate, modify something, and then some memory barrier to ensure that things are actually ordered, that I actually observe the writes or the reads before other ones. So if I have multiple threads all fighting for this mutex, all doing that test and set over and over again, that's the same memory location. I am actually going to trounce my performance because it's going to ping pong between all of them. It's going to invalidate all the other cores cache line, and they're just going to all invalidate all the other cores cache line, and it's going to be really, really terrible for performance. So we're going to have significant cache traffic, contention on the memory bus. Things are going to slow down because, well, all of them are spinning. They all have their own local cache at some level, and they all have to be consistent with the value main memory. They all, every time they try and do test and set, they would invalidate everything else, and it would be really, really bad for performance. So test and set, it's like essentially a store plus a memory barrier. So that's just going to make performance really, 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 really bad for our caches. So the more contention we have, aka the more threads all fighting for this lock simultaneously, the worse and worse and worse it's going to get. So that's why we have this graph, and now we know that while contention would severely degrade our performance over if we have more threads, we have more contention, possibly, depending on our application. And if we have a lot of contention and, well, we're trouncing our caches, we're going to make it even slower than if we had fewer threads because it's less likely that our caches would get decimated as badly. So we can actually trounce our performance with just having more threads over and over and over again. So now we can build some better spin locks using some things we know in this course. So some ideas we might have is like spin lock with backup or back off. So if the lock is held, just wait before probing again. So best performance, you could like exponentially back off, can cause fairness issues because, well, you're not guaranteed any ordering. You're still kind of fighting over that same spin lock. There's no set order as to what you get the, acquire the lock in order. So we'd have fairness. Potentially you could get unlucky and even have starvation in the very, very worst case. But here it would pause for like, I don't know, maybe a few microseconds, like 1 microsecond, and then it would just double the time it waits as it's more and more unlikely that it has to wait longer. And this is essentially what networks do all the time. Exponential backoff is like a very, very common thing in networking. So that's a strategy that's used a lot of the time. So that's one thing we have, but has a lot of fairness issues. And, well, we might get really, really unlucky with this as well. Also, it helps our cache line, but if they all are contending, it's still kind of bad. So one thing I can do is, well, instead of that, let's just have a spin in the cache and then only access that memory when it's likely to be available. So this is stupid, well, not stupidly named, but it's sillily named test and set. So the idea behind this is I'm just going to only read that memory location over and over and over again until it is false. And then once I know it's false, I will try to change it to true and then only have the bad in cache invalidation then caused by trying to actually do the store and do the update. So here I have a spin within a spin. So I spin while that value is true. And this here is only a read. So it won't have as bad of consequences for my caches if I'm only reading over and over and over again. So likely I will not invalidate the cache until it goes from true to false. And then atomically, they all kind of fight over who can set it from false to true to acquire that lock. But the idea here is we only try to do that test and set operation when it's possible we might have that lock. So we reduce contention a little bit, but we can still do a bit better than this. So first issue might want to resolve is the fairness issue because things aren't inquired in order. Something can, butt ahead of you in line. There's no set order to anything. So if we want to resolve fairness, well, we can ensure like FIFO order. If you try and acquire them in FIFO order and you're first in line, something else will not pass you in line. So the lock could actually have 2 counters. So it's like a ticketing system. So the next ticket, which would be incremented atomically, and then now serving. So, think of it as you're in line at, do people go to bakeries anymore? Ish. There's one place in Waterloo I know that uses this. What is it? Service Ontario still uses this thing. So think of this as Service Ontario. You get a ticket and then it serves you in order, more or less. Whoops, I didn't mean to draw that. So here, inquire, you would atomically do the fetch and increment. So you atomically pick a ticket. There's only one ticket machine. It's atomic. You take your number, and then you just loop over the now serving thing. So you spin. You only read over and over again until, well, you're up. And then, now you have that lock. And then to release it, all you do is just pick the next one in line. And again, this doesn't have to be atomic because, well, it's a mutex, only one thread can pass by the acquire at once, and you assume that you have it paired where each acquire ends with a release in order for something to get the lock. So we don't need an atomic here because there's only one thread that can execute this release at any given time. It has mutual exclusion, so no data races. So this reduces the number of atomic operations compared to the test and swap or test and set locks, but has some problems where that we can mitigate. So again, this will return that old value, and now there's like some weird things. We're still spinning a bunch of the time, and there's still some contention to that same memory location. So what we might want is that, hey, let's just get rid of this whole cache thing altogether, have something called a queuing lock where each CPU essentially spins on a different location. So release just unblocks the next waiter only because, well, for this one, all of them are spinning over and over and over again, even though they're far back in line. And we want to guarantee, like I said before, FIFO ordering, similar to ticket locks. We want to reduce the cache coherency and memory contention, so we have different locations, hopefully on different cache blocks, so we don't have any of the problem. And what we would do is just have like a lock that points to a tail of a list, and then in the lock acquire, we can add a node for the processor, so each processor has its own node, its own memory location. So there would just be one global lock pointer, and then, to acquire, you can be held, or you can set that pointer to your own data structure where you're holding the lock, and then you would add it to the tail and set up like just a sequence of CPUs that try and acquire that lock in whatever order. So in the lock release, it would just unblock the next node in the list. So there's no point waking up something that's like, third in the list or something like that. If it's not the next one to acquire that lock, why would I even bother trying to wake it up? And here the lock is, the lock here is just that next pointer that points to whatever it's currently running. And then running is the CPU that currently has that lock. And then these are other CPUs that are spinning, but they would all be to different memory locations. So one of the big implementations for this one is something called MCS locks. Those are a group of people's last names. Doesn't stand for anything other than their last names. So in this scenario, each thread has its own node, and that tail is shared by all threads. So there is a global tail that essentially points to whatever the last CPU is on that list. And in this case, let's say our queue was set up that thread 1 has that lock, and each node would have its own lock and then a next pointer. So thread 1 has that lock and points to the next node, which is CPU 2. That lock would be locked for them. They would be spinning on that value, and its next pointer would be CPU 3, which would have a lock that is currently locked. So it's spinning on that value, and then its next node points to nothing. And tail points to the last lock in the list. So now if we have, let's call them threads. Now if we have thread 4 trying to acquire that lock, well, it needs to atomically add itself to the tail and then atomically change 3's pointer to point to it instead. So how that will work is when process 4 or thread 4 comes in, it will atomically try to swap the tail pointer to its own node. So it changes this atomically to its own node. And then, well, it's going to have a pointer to thread 3 from swap. And then in here, it would have to change 3's next node to itself immediately. So right now, node 3 can't leave immediately because tail no longer points to 3. So otherwise, we would break our list because, well, if 3 points to nothing and then a tail doesn't point to it, We have now broken our linked list 3 has to point to node 4 in order for our list to be correct. So node 4 would have to link behind 3, and it would have to do that atomically, change that value, and we'll go over the implementation a little bit and what happens. So in that case where node 4 has added itself to 3's next, then it would have its own lock, and it would spin over and over again by setting the lock in its own node itself. So now when we release the lock, so here thread 1 has that lock and tries to release it. The steps we need to go to actually release the lock is, well, here all I have to do is look at my next. If my next does not equal null, that means someone else is waiting for that lock, and it's all in order. So CPU or thread 2 should be the next one to get that lock. So all I have to do, read my next field, it's thread 2, and then I would signal that directly, aka I would change its lock value from a 1 to a 0. So I would unlock it so it can actually acquire that mutex, or sorry, acquire that lock by doing the normal test and set thing. So now thread 2, when it runs, it now holds that lock. It is the only thing that tries to do the test and set because we changed only its local value of that lock. We didn't change a global value. In fact, the global tail that's shared between all of them doesn't even need a value of that lock. It just has a pointer to next. So now thread 2 has that lock, holds that lock, and whenever it releases its lock, it's going to unlock thread 3, and no other process is going to try and see that it changed or anything like that. They're all spinning on their local own local variable, or not, local lock. So some other things that can happen when it releases that lock, and it's the only process in the queue. So when it leaves, well, all it does is set tails next equal to null to indicate that, hey, nothing else is in the queue anymore. So some problems that it could have that we need to consider is, let's say process 3 has the lock and it's leaving as process 4 arrives. Well, what process 4 is going to do is try and set tail to itself. But process 3's pointer is still null, so it sets it sets tail to itself. So when node 3 tries to actually set tail to null, it will do it using an atomic operation. So because, well, the tail is shared between all of the threads, it's global. So it will do a compare and swap trying to set the tail to null, and it will figure out that, hey, I was not able to swap it to null because someone else changed that value. It is not currently null. So, or it is not pointing to myself. It is pointing to some other node now. So I can detect that and be like, oh, okay, well, it's no longer pointing to me. So instead of setting the tail to null, I should wait for my next to get set, and then when my next gets set, I can go ahead and unlock thread 4's lock. So 3 will now wait until that next pointer is valid, and then whenever it's valid, then it will signal thread 4, unlock it, and then it will be done with the spin. So that is the kind of case we need to consider for correctness. That's kind of the worst case scenario in terms of data races and all of that stuff. So this is kind of what the pseudocode looks like for it. So that shared variable tail, it's a pointer to the last, they call them Q nodes, and tail just stores the address of the last Q node. So there is some global tail that lives at some memory address. Oops, wrong pointer. That lives at some memory address here, and then we have acquire, and then that's my node, which would be local on that CPU. So first, it would set, my nodes next to null, then try to atomically get the old tail, make the tail point to my node, normal linked list implementation records, and it would do that with a fetch and store, which would be, the predecessor node that we should be changing. And then it would check, hey, if it's not equal to null, that means the queue's not empty. Well, then I should initialize the lock. I have that lock. I was the first one to get it. And then I would just append my node to the queue and then go ahead and spin over and over again until the predecessor sets its lock to false. So that's that case we just went over before. So some example here, if two threads both try to simultaneously acquire that lock, so say initially that the tail is equal to null, and then we have thread 0 and thread 1 here. Both their code would do the same thing, so it sets my nodes next to null and then tries to fetch and set the tail to be equal to my node, and then that would be the predecessor. So we don't know what thread is going to execute first, but since fetch and swap is atomic, then we know that, well, one of them is going to finish first. So if thread 1 or thread 0 finishes first, then, well, the old value of the tail is null since it was the first one to actually run and try to set it. So it would get a null back. So its predecessor is equal to null. So its tail can just can set the tail to point to thread 0. It was the first one to acquire that lock. So it now has that lock. And then after thread 1 executes it, it gets the old value of tail, which is a pointer to P or to thread 0. And then it's just going to spin on its own locked value. And then it would be up to thread 0 when it's done, when it does the release, to go ahead and set its locked value from a 1 to a 0 so that it can proceed. So under this scenario, no additions are lost. The queue might not be fully linked together until all threads actually complete updating its predecessor's next one. So changing the old value to update its next pointer. So we would have to be very, very careful with that to ensure we are correct. So in the release, what that would look like is it would need to check, hey, is my node's next equal to null? Well, if it's equal to null, then I have no known successor. So I need to go ahead and check if the tail still points to me. So that's the case where something else might get added after I check, and we do a context switch right here. So I do the compare and swap, trying to change the tail to point to from my node to null. So I know the tail's pointing to me, so I want to change it to null. If it returns true, that means, well, I've updated that tail to null, and I don't have to do anything. If it fails, then, well, someone else added itself to the list. I have to wait for them to finish. So I have to wait for my node next to not be equal to null, so I have to spin over and over and over again. So this release, again, might happen after that new thread adds itself to the tail, and then I have to wait for it to update my next node. So that is the scenario we have to consider here. So some things here we have to argue about simultaneously releasing and acquiring. So if acquire has completed that fetch and store and knows pred but has not updated it yet, and release sees no waiters and next is equal to null but knows acquire is in progress since the tail is not pointing to its own node, well, are any memory ordering instructions needed? And the answer is essentially yes. So if I am here and I know that the queue is not empty and I need to update something else, well, in here, when I release it, I have to wait until it actually goes ahead and updates it, updates my next. So this is the thing I need to be worried about in terms of memory ordering. So I need to absolutely make sure that this is complete, because the next thing I'm going to do is use that value, set its next, and locked equal to false, and update it. So the memory ordering I need is in this while, I want to make sure there is a read barrier here, essentially. So I need to make sure there's a read barrier as part of this while to make sure that I actually have the most up-to-date read here. And here when I read it again, it is actually up-to-date. It doesn't have any coherency issues or anything like that. I don't want to read a stale next here. So I would need a read barrier as well. Normally you put it as part of this while. So like while, and then a memory read, and then have it spin over and over again. Whew. So everyone good? That was fun. Yeah?
I'm a bit confused. The queuing lock thing that we saw, that solves the cache performance issue?
Yeah, so the queuing thing is basically, this is like a good implementation of the queuing thing. So
and it solves that because we're not repeatedly test and setting this like global variable?
Yeah. Yeah, so everyone is essentially test and setting their own lock value. Okay. So each thread has its own lock value, which would just be an int like 0 or 1, and its own next value.
I see. So we don't need to, when we're doing that, we don't need to do that atomically. We just need to do the initial tail acquire thing atomically?
We still need to do it atomically because another thread will be setting it like our lock value whenever it's done from a 1 to 0. Okay. So we still need to do it atomically, but the idea here is like here, every thread is spinning on their own value. So like this tail is global, so that's like our next pointer. And then on each of these threads, it has a next pointer and then its own lock value, like its own int. So.
Sorry, could you go to the code, the acquire code? Yeah,
yep.
When you do the while my node lock, that's not atomic, right?
Well,
the very bottom when you're spinning, that part's not atomic.
Yeah, so that part's not atomic, but it only gets updated once, so it's okay. So it only gets updated by the thread that actually changes it from true to false, and only one other thread will do that, and that means you have acquired that lock, so you don't have to worry about a data race in that case. Yeah.
You explained on the latest slide you were talking 31 about the simultaneous. Yeah.
Yeah.
Can you explain the read barrier again for that while loop and release?
The read barrier here, yeah. So basically, like you do not want it to like, especially it gets really weird with like branch prediction and stuff. So if it predicts it's not equal to null and then tries to use that value and uses this, it'll just do something really weird. But here, I think you do need a read barrier here. I might have to go over it and show a better example than that. That's better thought out than this. But I'm pretty sure that there does need to be a read barrier there. I'll try and go over it and see a better example of it too. Yeah.
Can you explain how the read barrier would work and what it would do here?
So the read barrier would essentially make sure that, between these reads, this operation, this read completely happens before this one. So I know that it's for sure not equal to null. It is the most up-to-date value before I actually use it on this line here. That's essentially looking at it generally what you need to have for the read barriers there. So some ordering between them. We don't want some old stale value or anything like that. All right, so that type of lock, in conclusion, it needs a bit more space than normal mutexes. So the space it needs in terms of words, it's 2p plus n. So this n is for each lock. It needs that next pointer, that global next pointer. So that's one word. Word is just the size of a pointer. And then each process has its own copy. So it needs a pointer, so its own next, and then the lock itself, which would be also a word. So each thread, instead of p, we could call them threads. So each thread needs two words, pointer and the lock value, and then each lock just has one global next. And this requires that it has a local queue node that's passed as a parameter. You could also dynamically allocate them if you really want and look them up in a table. That has to do with the implementation. But for all this, we need atomic primitives like the fetch and store and compare and swap. And the main idea here is we only want to spin on local locations, so we don't want to thrash the cache or anything like that. Only spin, each thread spins on its own value, its own memory location, so we don't have any contention issue and memory traffic issue. So these are used all the time. Monitors in Java, they're variants of MCS. The Linux kernel uses them all over the place, and their implementation is quite readable too. All right, what about Pthreads? So Pthreads, the basic lock there is pthread mutex t. Probably have used it all the time. So how is it actually implemented? It's kind of like a mix mash of techniques because it does some more complicated stuff. So first, it does like that adaptive number spin using test and set. If that's not successful, it adds itself to a linked list and suspends itself, so it yields. And it's a bit similar in structure to MCS locks, but it's a bit more complicated because it also adds other things like waits. You can set a timeout on it if you want it to stop trying to acquire that lock, and you can set priorities if you want, you know, some threads to acquire the mutex before any other threads. And that unlock, what it will do is ensure that priority actually is obeyed. So it would wake up that waiting thread with the highest priority if there is one. So that would have to work in tandem with the operating system because we need thread sleeps and wake ups and all that stuff. So some parallel programming techniques. If we have a counter used by a whole bunch of threads, so we have like counter plus plus, well, this is actually a load followed by a store. So simplest case is it would need its own critical section. So we lock a mutex, we do counter plus plus, unlock. That is straight out of, you know, the operating system example. But that's only if the exact value is critical and you don't want any data races for it. If you want a cache friendlier approach, like if the number of increments is way, way greater than the number of reads, then, well, you essentially do like a map reduce type thing. So you give each counter a local variable per thread, properly padded so we don't have any cache line issues or anything like that. Have them all increment their own local counter so I don't have any locks needed. I don't have any data races if I'm only updating my own copy of the variable, if there's only one copy of it. And then I don't even need to approximate the number of reads. If I sum up all the counters in a non-data racy way, I could use a lock here. It probably wouldn't be that long. Then I could just sum it up, get that final value. Or if I want to approximate it, I don't even bother with the locking at all. I let data races happen, and if I miss one, oh well. That's like there's actually a whole funny line of research called approximate computing, where to speed up some things, it just like skips operations. I believe I read one paper that was pretty good, where like to speed up a for loop, you just don't do half of it, and surprisingly, programs still work. So is it really that necessary? Who knows? And then, yeah, and then you can also have barriers. So you could have n threads, get to that barrier, and then do that to actually synchronize all the values between them. That's more or less what GPUs do. Hopefully, if we have time in the course, we can go over some GPU programming at the end of it, which is more parallel programming stuff. But who knows if we have time. Hopefully, that's what I want to put in this course because it seems weird that it doesn't have it. So some other things. So structuring data for caches. Well, any read, like mostly read data, like you want to separate out what's mostly read and what's frequently modified. So, you know, if the linked list payloads or if something gets modified often, then hopefully I want to have separate pointers and things like that. Exact opposite of what I want to do on a single uniprocessor system, because again, caches are our enemy here in terms of performance. So I want to segregate anything independently accessed from each other in different threads. I want to make sure it's on different cache lines so I don't have that false sharing problem. And I should also use per core data wherever possible, like one ready queue per core on Linux, and like JE-malloc, that's one of the techniques it did too, just to ensure that there's no false sharing or anything like that. And if I have write mostly data, I want it to be private. I want to try to only write to my own local copy of it, and then everything will be nice and fast. I don't have to worry about data races or anything like that. And if I'm locking data, well, I probably want like per core reader writer locks for like read mostly critical sections. So for read access, I can acquire a local lock. For write access, acquire all locks. Writes would be expensive. I don't know why it's not in the slides. There is a mutex read-write lock that you can lock for reading and lock for writing, and that will allow multiple readers all at once or only a single writer. So if your data is like that, I would say use a read-write lock. And then we might also want to like move any contended locks from its associated data so that I don't have any cache interferences where me modifying the lock also modifies the cache line that the data's on or anything like that. And there's more resources in case you are interested in this. Michael Scott, not the Office one, has a whole bunch of implementations of it. You can actually read, if you just Google, whoa, that's a huge red pointer. Wow. I don't know how that happened. But if you just Google like Linux MTS lock, you can see the Linux implementation of it. I guess this is fairly old, probably needs to be updated. There's an atomic operations project, but like C++ 11 and friends have atomic operations on like integers and stuff that will atomically allow you to increment it and decrement it and all of that fun stuff. So you don't have to worry about data races for that, and that's usually for simple like primitive values. So with that, I will stick around. That's again really huge for the extra 8 minutes, and we can see what we can get through with that. So just remember, pulling for you.